Thank you all for joining us today. My name is Sean Maurer. Joining me today is my colleague Ryan Siegel. We're going to be reviewing the zero codes and application of renewables to facilities. A couple of housekeeping notes as we're letting people trickle in here. If you do have a question during our presentation, please use the Q&A window to enter your question. If you enter a question in the chat, we may miss it. If you put it in the Q&A window, we can be sure that we will see that question coming in. If you hover over the top center, bottom center of your screen, you'll see that Q&A option available. We will also have some polls as we go through the presentation here just to check comprehension and that we're covering some of our content appropriately. Also, credits will be available for this presentation. Once we've concluded, you will receive an email with the presentation slides and a link to a form to enter your AIA information. And that way we can provide you with continuing education credits. Our presentation is brought to you today by AIA Illinois and the Illinois Green Business Community. Joining us here briefly at the start are Stacy and Brian to do just a brief introduction. Stacy, if you want to go ahead and take it away.
Sure. Thank you, Sean. Hey, everyone. Stacy Finkston with AIA Illinois. So glad to have you with us today, and I hope everyone's having a great week. I'd like to thank Sean and Brian for this informative series today, and the CDAC team for putting this on, that we're a proud sponsor along with Illinois Green Alliance, a valued partner of ours. Don't miss out on the next one, which is May 19th on Passive House. We'll be promoting that this next month to register for that. Also, I want to let you know that tomorrow morning at 8:15, in honor of Earth Day, we'd like you to join us for a coffee talk, a free webinar discussing AIA's 2030 commitment. If you or your firm haven't committed to 2030 yet, please join us and find out how it helps your firms, your clients, and our planet. I'm going to put the link to sign up in our chat. Again, that's free. It's going to run from like 8:15 to say 9-ish. It's going to be a great way to celebrate Earth Day and to start your weekend. So now I'll hand it on over to Brian Imus of Illinois Green Alliance to say hello. Thank you, Brian.
Thank you, Stacy, and I really appreciate having a couple of minutes to introduce Illinois Green. And thank you to CDAC for hosting education programs like this. It's really valuable to the community and to our members as well. For those that aren't familiar with Illinois Green Alliance, we were founded 20 years ago. We're celebrating our 20th anniversary. And when we were founded, it was a ragtag team of architects and engineers and contractors who are really excited about this new thing called the LEED Green Building Rating System. And we did a lot of work over 20 years to promote that rating system. Looking to the next 20 years, it's all about net zero. So what do we need to be doing to make net zero buildings as common as LEED buildings are here in Illinois? For us, we're thinking about how do we leverage our members and the community here of green building professionals to demonstrate that net zero is possible in any building type. Educating policymakers so we can truly scale the technologies and the design practices that we know work, and of course, a lot of professional education. And that's where I'm thrilled to be able to partner with CDAC and AIA Illinois on education programs like this. So I'm glad that you all are here today. So a lot of opportunities over the coming year as it's our 20th anniversary to connect with our members. And I'd encourage everyone to learn more about some of the work that we're doing by going to our website at illinoisgreenalliance.org. And I'll turn it back to Sean. Thank you.
Thank you both. So as I noted, presenting today are myself. I'm a senior engineer at the Smart Energy Design Assistance Center, and Ryan Siegel, who is also a senior energy engineer at CDAC. As I noted, we do have continuing education credits available for both the IECC and AIA from today's presentation. Again, you'll receive a link in an email at the end of this presentation for your AIA credits. We'll make sure to turn that information in for you. Who we are at CDAC, we are an applied research program at the University of Illinois, housed at the Urbana-Champaign campus. And our overall mission is to reduce the energy footprint of Illinois and beyond. And these presentations on energy efficiency for buildings, energy code, and a number of other resources are just one of the means we have of reducing the footprint through education. One of our newer programs is the Building Energy Education Fundamentals for Architects. If you wish to learn more about this program, you can visit our webpage at smartenergy.illinois.edu/events. This is a program with content developed around community college training curriculum. So it's kind of basic level energy information for architects and engineers. Get my audio. We highly recommend that you look at that website and that information, see if it's helpful for you. Also, if you're in contact with professors or anyone at previous universities, then please let them know this information is available and see if it's helpful for them as well. At CDAC, we also provide technical support for energy code assistance. We have an email address, energycode@illinois.edu, and a 1-800 number that you can call for quick assistance. We do prefer that email address is used. It gives us time to discuss within our office your question and get you the most accurate answer possible. But that 1-800 number is available if you need a quick response. We also have a number of online resources. As I noted earlier, we have the Building Energy Education Fundamentals. We also have previous blog posts, website links, links to our previous workshops and webinars, and links to the energy code documents themselves. So you can access the 2018 IECC, and when the 2021 IECC is adopted by the state, we'll have that link available on our website as well. We also have links directly to the Illinois amendments to the energy code and the Chicago amendments to the energy code at our useful websites link. So a one-stop shop for all your energy code information. We also host a number of smart tips and newsletter articles in our Building Energy Resources page. So there's a lot of good information there to help with energy efficiency projects and ideas for your facilities. But today we're going to focus on the zero code and understanding the requirements of meeting the zero code for new buildings and existing buildings. And then we'll look at understanding why we want to do energy efficiency first in buildings and minimize how much renewables we have to install to offset our energy usage. So first, our goal to zero. So here we see the path of AIA's 2030 challenge, which sets the goal of net zero energy facilities by 2035. As we see here, being at 2020 and 2021, we're in that 30 to 20% range target for energy use in buildings, where they're going to use 30% of the baseline energy consumption, which I believe was, Ryan, do you remember which energy code that's based on?
That's based on the CBEX 2003 is the baseline for that.
But to reach those targets, the 2030 challenge, here we're showing kind of the site EUI targets to reach those reductions. So the 70% reduction and the 80% target reductions. You can see these are quite substantial targets to hit. They're quite low energy usage for a lot of facilities. One of the things to note is like looking at convenience stores, gas station facilities, having that target energy consumption of 72.4, and then at that 80% target dropping down to 48.3. So it's quite difficult to hit for a facility that's, it's got a lot of lighting, you've got refrigeration equipment in that building, cold food storage. So it's a difficult target to hit, but with improvements to technology and efficiency of systems, lighting systems. We're getting much more able to hit these targets, but it is a significant lift for design and facilities to hit these lower targets. So how does the zero code help? Well, the zero code and the IECC Appendix CC or RC, depending on commercial or residential buildings, for the zero code just requires that the building comply with the minimum requirements of an energy code or standard. They do have language written into them that you can use an advanced code, such as the 2021 International Green Construction Code or ASHRAE 189.1. But the baseline requirement for the zero code is that you meet the baseline energy code in effect for your area. So for us coming soon, that's going to be the 2019 ASHRAE 90.1 or the 2021 IECC. They do have the ability built into that zero code to do modifications to it to advance energy efficiency and the ability to apply renewables to buildings. So they do have language in that zero code to require site electrification, removal of on-site combustion, as that will negate the carbon offsets that are required for on-site combustion through purchase of renewable credits and offsets. And it can also be, as I noted earlier, modified to use more advanced energy standards through some language built into that code that says if you're going to use a more efficient standard, insert those standards in this portion of the code. If you want to enforce a lower target for your building, then the code has language built into it where you choose your target and calculate what the energy efficiency is going to be. If you're doing performance modeling, they'll have target EUIs reduced by that designer's chosen target. If you're using Appendix G, then there are performance factors that are adjusted by that design target as well. So it's structured, even though the minimum requirement is to follow the minimum building energy code, it is structured that you can input advanced codes into the zero code standard. As far as renewable energy requirements, it simply requires that on-site and off-site procured energy must exceed the minimum load used at the site. The way that's figured in the energy code, if you're following a performance path like Appendix G or one of the energy cost budget methods, you simply use your calculated budget building's energy usage and offset that energy with on-site and off-site procured energy. If you're following a prescriptive path, they have calculated a table of energy use intensities for different facilities. We've put a sample here of that table for climate zones 4 and 5 in Illinois. So you kind of get an idea of the types of targets they're looking at for those EUIs. You would get similar EUIs if you modeled the standard reference design building that's required for the performance path. Should get you close to what these targets are. So that's how it's figuring out what your load requirements are to figure out how much renewable energy you need for your site facility. For on-site renewables, the zero code is pretty straightforward. The energy produced directly offsets energy needed at the building. For off-site renewables, there is an adjustment using a procurement factor. That procurement factor varies based on the type of procurement that you're using for your offsite renewable energy. It's going to account for grid losses, accounts for the potential that your procured energy is going to result in the addition of new renewable energy deployment. So the expansion of solar, wind, hydroelectric, various other renewable sources. And it's going to account for the potential of building owners as they, buildings will change ownership over time. There is the potential for them to opt out of renewable certificate agreements. And so you then lose the benefits of that renewable credit for that facility. So As we look at the Ashrae standard here for the zero code, this is the table of their procurement factors. But what we see is the range is from about 50% down at the bottom there for direct purchase of unbundled RECs to about 90% for procurement factors that are a little more stable and have more potential to have direct impact on building energy consumption and less of the risk of those RECs or credits being lost over time. But what this means is when you're calculating your building's energy use, you're going to have to increase your energy use somewhere between 10 to 100% of what you calculate the building's energy load is going to be in order to account for these procurement offsets. And if you're procuring from multiple sources, then you're going to apply these individual factors to those various sources. For the IECC in the CC appendix to the International Energy Conservation Code, much less number of factors to look at, but they are much more stringent. So they're, you can see here where Ashrae, they had a 90% offset factor, so you only would have to increase your procured energy for offsite renewables by about 10%. Here it's a 75% procurement factor, so you're gonna have to increase by 25%. And then for unbundled RECs, where Ashrae's that minimum was 50%, here it's a 20%. So significantly larger renewable requirement if you're following the IECC zero code component versus the Ashrae component. For those offsite procurement requirements, when you're looking at the zero code or the IECC's zero code amendment or appendix, they both have the same requirements as far as how are you going to document the offsite procurement of renewable energy. You have to provide documentation to the authority having jurisdiction. The contracts for those renewable credits have to be applied for a contract with a duration of 15 years at a minimum. And it's applied to the building, not the building owner. That way, if the building is sold and transferred off, the credits still apply to the property. Energy sources are specified as wind, solar, or geothermal. There are some exceptions for renewable gas, biogas sources, and new hydropower, not existing hydropower. Again, the goal of the net zero codes is not only to ensure that buildings are reducing their energy consumption and carbon offsets, but also that as we're doing that, we're expanding the renewable energy portfolio and not using existing renewables that are already accounted for in our electric grid. So there's an additive requirement to offsite procurement requirements. So before we move on, we do have a quick poll question here. Our first question, the zero code requires buildings be how much better than the minimum energy code before applying renewables? 10%, 15%, 20%, or they just have to meet the code minimum performance? And then the zero code and the IECC appendix use the same procurement modifiers. Is that true or false? Give that a couple more seconds. Seems like we got a few more responses coming in. Okay. Looks like on our first question, everyone picked up on the zero code requires at a minimum, you just meet code minimum performance requirements. They do not require you to have advanced energy efficiency in your buildings. Just have to meet that code minimum requirement. And then the zero code, which is Ashrae based, and the IECC Appendix CC do have different offsite procurement modifiers. Ashrays were a little less stringent than the IECCs. IECCs were much more stringent modifiers. So they are different. It will be important for following zero code in the future. With that, I will turn it over to Ryan to discuss how we impact our loads.
Well, thank you, Sean. And something we're definitely going to be touching on here and kind of hitting heavy is, the importance of impacting our loads before we add our renewables. And part of this is just from the sheer aspect of trying to meet net zero just by putting renewables on site. Oftentimes is really not generally practical. But fortunately, there are a few factors out there that can really have a substantial impact on energy consumption. And as we notice here, a lot of this generally is envelope related. And so understanding that the envelope is defining the boundary between inside and outside. And so if we don't have a good boundary between that, and you end up with a lot of energy leakage between the inside and outside, that makes it much more hard and difficult to reach. So looking at building orientation, best practice out there is to try to limit east-west exposures for buildings, particularly because these are the facades that get heavily loaded with sunlight and sunshine exposure, particularly in the morning and then the afternoon. So in the morning, the east side is going to be heavily loaded with solar gain, and then in the evening, the west side is very loaded with solar gain. So looking at this facility here, we can see this one, the building was oriented north to south, which then places a large eastern exposure here, the front facing east, and just all this glazing. It's a beautiful building to be in the morning, just from all that sunlight that streams into the building. But this can cause a lot of issues with glare, and again, all that solar heat gain having to be made up. Fortunately, this building is totally open inside. It's for equipment and offices, such that you don't end up with a dramatic imbalance in that gain. That gain coming in from the east for this facility is able to make it all the way through that building, so you don't end up with the east side being hot in the morning and the west side being hot in the afternoons. Once we've kind of tried to orient our building well and place fenestration in a good orientation for us, is looking at the actual fenestration performance, and understanding that even the best windows out there really make for poor walls as far as from an insulation perspective. And so here, understanding that the code calls for fenestration of a U factor of no higher than 0.36, which is just a little under an R3 equivalency. Even best in class that we're finding on the market here is substantially better at about a 7.7 R value. However, even a code wall minimum for opaque walls is 15.6 R value. So best in class is 3 times as good as the minimum standard, but it's still only half of what the wall is really needing. And just so from that aspect is trying to make sure that we're judicious about where we place fenestration, and trying to make sure that we're trying to get this move towards this best in class. Again, when you say you're losing 2/3 less heat out the best in class windows, that's going to have a dramatic impact on energy consumption. As part of this is fenestration orientation. As noted earlier, trying to perhaps minimize or not try to include a lot of east and west facing glazing, but perhaps using more the north and south faces. You know, north gives it a nice even light during the day, but then you end up losing a lot of heat during the winter. Southern glazing, you can get much more heat load from that, but you can use that to your advantage throughout the years. Something I should mention is one of the proposed amendments working their way through the state of Illinois is for buildings that do have larger east and west facing glazing relative to the north and south facing glazing. They're actually going to be requiring better solar control and performance of that fenestration. So if your building is heavily east and west glazed, then you're going to have even better windows than what the code calls for. So again, solar heat gain can really be a benefit to you when you want it, but it can really be a detriment if you allow it into the building when it's not desirable. You know, trying to bring in that streaming sun into that summer, that's really going to put a heavy load on your mechanical systems. And as part of this is also looking at, you know, what are we doing for shading and landscaping? You know, you look at a lot of older buildings in developed areas, and you'll see, you know, we look back to even the Victorian era. You know, they used a lot of shading in trying to use that to their advantage to help keep buildings comfortable, because that's the other side of this, is looking at comfort and resiliency. And so here, comparing two different buildings, you know, the building on the left looks to have a fair bit of trees and plants doing some shading. But this can also be done through the use of architectural features and other ways to shade fenestration, so that, again, trying to minimize that summer gain and take advantage of that winter gain. Whereas if we look at a building on the right here, built, looks like probably in the 60s, maybe 70s, we see a lot of glazing, and there's almost no shade on this building at all. Either natural shading or architectural shading. And so the only real architectural shading that they've done here is kind of stepping back that first and second floor glazing, so that third floor is kind of trying to shade that glazing. This building we've looked at, and from talking with occupants, they've had a lot of comfort issues in this building. You know, again, part of that is the glazing from the 60s and 70s. You know, it doesn't perform even as well as, you know, code minimum today would. So the other aspect that's really coming into play here recently in commercial is understanding that air tightness plays a very big role in energy consumption, comfort, and resiliency. Residential buildings have been required to be tested for several years now, going back almost a decade that it's been required to have buildings tested for air tightness in residential. Commercial, this is fairly new, and something that when you're going through and looking at design, to understand what the testing protocol is for air tightness, and trying to make that testing easier to accomplish. Some of the big aspects of this is being able to cover all the continuous ventilation system openings. So for a lot of commercial buildings, that's done through rooftop units and air handlers. And so you have these large openings that you have to be able to try to seal up in order to perform this testing. In the upcoming codes, air tightness testing, and also known as envelope commissioning, is becoming going to be required for the state of Illinois. So any new commercial buildings built beginning perhaps later this year or with construction beginning in 2023, you're going to be required to test this. And, you know, again, part of this is if we're not, if we don't have good air tightness, and again, that good definition between the inside and outside of our buildings, you know, with any of that air that comes through in our region, oftentimes you get a lot of moisture transfer, either humidity entering the building in the summer or leaving the building in the winter, and trying to avoid having that moisture condense inside that wall. So this is a big piece coming, and this air tightness, that impact on the building is part of the reason why the Government Services Administration, or GSA, for the federal government and the Army Corps of Engineers has been requiring air tightness testing on all their new construction for several years now, because they were finding that without testing it, there were a lot of problems going unseen. And this testing, trying to manage to do this as soon as you can in the construction process, as soon as the envelope is complete and all the planned penetrations through that envelope have been made and sealed back up, getting that testing in before you cover up everything. So once we've got a really good envelope, that's when we start turning to equipment efficiency. You know, lighting has been a dramatic improvement over that. Over the years, previously, you know, we saw lighting 1 watt per square foot or higher. We are now seeing lighting designs in the 1/4 to 1/2 watt per square foot range. And with that, you know, again, HVAC equipment, we've seen dramatic improvements, and even ventilation, energy recovery, doing energy recovery for ventilation air. We're now seeing best in class recovering 80% of that energy in that airstream, which if you're recovering 80% of that energy transfer, you know, making up that last 20% doesn't take a lot of equipment, which means you now have smaller equipment, smaller ductwork, and the like. So those can be some dramatic changes on your quest to net zero. And as Sean mentioned earlier, you know, that 2030 challenge, we are definitely getting into some very tight tolerances now. You know, being forced to kind of really step up our game to achieve those. So with that, I believe we've got another poll here.
The poll will be at the end of the next section.
Oh, sorry.
But we do have a couple of questions if we want to address those before we move
Sure.
on.
Yeah, let's touch on some questions here. I did also see a note that came in regarding fenestration and potential conflicts working with computer screens. I know I certainly have seen that conflict depending on where I'm working, whether the window is you know, in front of me or behind me. You know, that's a real big concern to look at.
Yeah, glare control is important. We did have a question about one person thought the south elevation had the largest solar heat gain, which is true in terms of energy addition to the building over the course of a year. But as far as instantaneous loads added to a building on an hourly basis, that east and west loading is very high because the sun is hitting directly through that glazing, where on the south side of the building where the sun's had time to rise into the sky, you've got a more indirect glancing blow of those rays hitting the glazing, a little bit more reflection that happens there. So the instantaneous loads are what's going to be larger on the east and west side. And then your your mechanical systems have to compensate for that, and designing around that can be difficult and lead to upsizing of equipment that otherwise might not be necessary. And then we had a question about how does envelope air tightness work with new requirements for ventilation due to COVID-19. The big thing there is you want to control your ventilation through a mechanical system. So you're still going to provide outdoor air, but you want it to get filtered, so you're removing any outdoor contaminants. You want it to be dehumidified or humidified as needed, so that you're maintaining space comfort, where if your envelope's leaking that air, it can bring in outdoor pollutants, car fumes, pollen. Out west where you got forest fires, you got that smoke that can come in with that kind of air. So you want to make sure it's going through a mechanical system, getting filtered and cleaned, and then conditioned so that it's providing comfort to the space. And again, if it's leaking through the envelope at an unconditioned rate, now you've got a higher load that your mechanical system has to take care of as well. So your mechanical system is going to end up being sized larger to handle that ventilation load. So it's the ventilation is still going to be there for your buildings. It's just going to be designed through the mechanical system, so it's controlled rather than uncontrolled through the envelope.
And that's a big issue as far as people have begun to understand, the importance of building it tight and ventilating right. Is if you're relying on the envelope to leak for your ventilation, the issue here, particularly in the state of Illinois, is the inconsistency of wind and weather. And so when it's very windy out, your building will really be ventilated. And when the air is still outside, then that envelope isn't going to really be leaking that air through that. And so understanding that we want to, people say that buildings need to breathe. We want them to breathe consistently every day of the year and not just on windy days. So that is something else that we have seen a substantial impact from, is with the new guidance on ventilation, and encouraging improved ventilation and increased ventilation rates through that. That makes that energy recovery that much more important to do on that. And again, so even if if you're recovering 80% of the percent of that energy, doubling that ventilation rate is not going to penalize you nearly as bad as it would have previously. Too often we have seen in existing buildings ventilation being done at the air handlers with no energy exchange at all. And so that can be really detrimental and really heavy load on that. So once we've kind of addressed our envelope and really trying to get our building to perform as good as possible, then looking at, how are we going to offset that energy that we are using? And so we're going to be looking at a few different things. Renewable energy credits, also known as RECs, or SRECs for solar renewable energy credits, be it through on-site or off-site renewables. And then the alternative is to look at emissions or carbon offsets. So with that, understanding that there's definitely a difference between these two. Offsites, looking at any policy or technology that we're avoiding reducing greenhouse gas emissions. So offsets could even be things such as, I'm not going to cut down these trees as part of the, I'm going to keep these trees growing, and so they're going to continue to sequester that carbon. And I'm going to take advantage of that emissions gain and monetize that through these carbon offsets. So again, this is policy or technology, could be avoiding or reducing. That's been part of the discussion as far as, do we pay to keep oil and other fossil fuels in the ground, and say, you would have extracted those, but I want to pay you to keep those sequestered. As an alternative to offsets, we can look at renewable energy certificates. So this is a certificate specifically for electricity generation, and it has to be able to be tied to a renewable source. So this is solar, wind, could be biofuels. That gets a little quirky. Hydro. So this is around electricity generation around a renewable source. And then this is the certificate is, I'm claiming those kilowatt hours that were generated, understanding that we can't necessarily, the grid doesn't differentiate between green energy and non-green energy, but the certificate kind of is more of an accounting thing for that. So, as far as looking at offsets, we can do sequestration. So as I mentioned earlier, either trees or growing of plants, CO2 injection. This has been carbon capture and sequestration from power plants. Has been a lot of there's been a lot of news around that. As far as the practicality, that has been a little bit more difficult to do. Could also have thermal renewables. So this is your biomass and biofuels, saying we're gathering these from a sustainable source and a renewable source. And then looking at transportation offsets, transitioning from gasoline to electric vehicles, that can be can produce some carbon emissions reductions, which some people may choose to monetize those. And then also, what are we building buildings out of? If I choose to change from concrete to timber frame buildings, there is a reduction in carbon emissions from that. And so again, carbon offsets tend to be a little bit less tangible and a little bit squishier. Whereas if we're looking over at understanding that some of these offsets are renewable, some are not. Biofuels, you can do a reduced carbon, but once you use them, you've kind of used them. And so some of these offsets are just, I'm going to choose to do something. Again, kind of thinking about, am I going to choose to not drill the oil or extract the oil from my property? That's really only a one-time thing. Once you've paid me to not extract it, well, I can't sell someone else to not extract the same thing that you bought. So there's definitely some difference here. So with that, I just want to make sure that we've covered differences between renewable energy credits and offsets. So what is the difference between a REC and an offset? Are they essentially the same? Offsets are policies or technologies that avoid greenhouse gases, and RECs are market-based for energy or electricity. Offsets are a type of REC. RECs aren't always renewable. Offsets are always renewable.
And the major takeaway from the message here, as we're getting some responses in, is that the zero code is dealing primarily with renewable energy credits. Offsets would be a separate component of net zero goals outside of the zero codes.
Right. Looks like most people have answered here. All right. Okay, good. Most people picked up that yes, offsets are policies and technologies RECs are market-based attributes for renewable electricity. So,
A couple of answers there for usually RECs are considered a subset of offsets, not the other way around. So that's kind of a reverse statement there. Really, they are separate things, but sometimes in discussion about building renewables and energy, renewable energy credits will be listed as an offset of buildings' energy use. And then RECs are always going to be renewable. They're coming from solar, wind, geothermal. Offsets are the ones that are not always renewable. They are carbon reduction strategies, not necessarily carbon neutral strategies.
and with that, well, Sean, take it away.
All right, thank you, Ryan. So we wanted to touch on the advantages of minimizing renewable demand, why we want to focus on that. Part of it is the relative cost between installing new renewables and making buildings efficient. And then we'll touch on some grid impacts, maintenance and upkeep, and end of life costs for building efficiency versus renewables. Just on a cost basis, here we're looking at the basis for utilities. Funding energy efficiency projects in general is going to be more economical than renewables. There are some more energy intensive energy efficiency projects like whole envelope upgrades that usually have longer payback periods or higher associated costs. But in general, improving energy efficiency for buildings is going to be a lower cost option than installing utility scale or even local scale renewable energy. So looking at kind of the relative cost for building owners, renewables are going to require additional equipment added to the building. It's going to add to maintenance costs and labor. And if you're using offsite, now you've got, it's a reduced utility cost, but you do still have a utility cost associated with that energy consumption. Whereas energy efficiency can be implemented as a normal part of a building's maintenance budget. So it, if you design efficiency into your building, it doesn't necessarily have to increase the maintenance load on the building owners to upkeep that efficiency. So looking here at kind of the unsubsidized costs compared to efficiency costs, you can see that at the unsubsidized rate for residential, it's about half. For commercial, it's slightly less, about 10–15% less. But it does depend on the measure and what's going on. What you're looking at on the chart here is electric only utility savings from efficiency. If you start factoring in efficiency impacts on gas consumption, propane consumption, and fuel oil consumption, then the Northeast falls in line with the rest of the nation there as well. But there are a lot of non-energy benefits to improving building efficiency as well. You've got higher environmental satisfaction from the occupants, improved health overall as you're controlling the risk of mold and mildew, you're controlling the air quality better. You increase the productivity of the occupants with good designs. The longevity of the building and its systems is improved through better efficiency, and long-term and short-term maintenance costs are also reduced. Whereas if you built kind of a standard building that has some of the typical inefficiencies associated with it, and then you add renewables to it, the building still has those intrinsic inefficiencies. You still got occupant discomfort next to drafty windows and things like that. That over time are going to increase the maintenance and operating costs of that facility and kind of offset a little bit of the benefit that you get from installing those renewables. Just looking at some of the added maintenance and upkeep, for solar panels, you got to clean them a few times a year, get the pollen and dust off if the rain hasn't fallen in a while. There is the potential for storm damage from wind and hail. Although with improved panels now, that's greatly reduced, it is still a possibility. But the big component is the inverters that convert the AC power or DC power to AC power so that you can grid tie these systems. And usually those are where most of your failures are going to be, is on that electrical side. So there is a maintenance and upkeep cost. The more renewables you have to install, these inverters and radiators, you have to install more of those components. to connect those loads together. And so the more you have, the more potential failures you have, the higher maintenance upkeep that you have as well. And similarly for wind sites, if you do have a wind turbine at your building, you've got this large device that you've got to do maintenance on. A lot of times we've seen that these wind turbines just, they run for a few years and then a mechanical problem happens because they aren't getting the regular maintenance they get as part of a utility scale implementation. And so they do have to be maintained 2 to 3 times per year. You've got to have either cranes out there to lift heavier equipment if they're doing a drivetrain replacement, something like that. Or you've got to have specialized crews trained for high altitude maintenance work, working on these devices. And so there is an associated cost for maintenance and upkeep that if we can reduce our loads up front, reduce how much additional renewables we have to install, we also reduce these maintenance costs. For buildings themselves, better efficiency doesn't necessarily mean that you're going to increase the maintenance load for the building. A lot of times, higher efficiency is going to reduce your maintenance loads. A great example Ryan's already touched on is if you improve the envelope, you're reducing air leakage through that envelope. You reduce the risk of both water leaks and condensation damage in that envelope, which can extend the life of the structure almost indefinitely. For HVAC and lighting systems, if those are properly sized and installed with proper controls, there's less risk of short cycling. That reduces the efficiency and lifespan of that equipment. The one kind of trade-off here is that as we've made buildings more efficient, we've started installing more controls. The additional sensor maintenance load does increase slightly. You know, you've got multiple points in the building now that you've got airflow sensors, temperature sensors, and those things do need to be calibrated or replaced over time. If you're using wireless sensing technology, you've got batteries to maintain. So that is kind of the one trade-off with improved efficiency. If you're doing advanced controls in buildings, you may have slightly higher maintenance loads over a typical building for those control devices. But if you're doing a good design and you're trying to simplify that control system as much as possible, you can mitigate that or, again, even reduce the maintenance load for facilities. So unlike renewables that are adding more equipment to a building that needs to be maintained over time, built-in efficiency is not going to add that additional maintenance requirement. You're not adding more things. It's, you know, an efficient building and an inefficient building are generally going to have the same building components to maintain. And so the workload overall shouldn't change that much. We do acknowledge there's one exception as buildings are taking more and more advantage of different efficiency strategies, and that is dynamic envelopes. You've got more moving surfaces, little actuators and things for shading devices. That's going to dramatically increase the maintenance load for an envelope. You've got a lot more failure points, things that can go wrong there. With double skin envelopes, it depends how they're deployed. If you've got some automation involved in those to take advantage of natural ventilation, then you've got dampers and vents that have control devices on them that's going to increase the workload a little bit. But otherwise, the main difference is you've got an additional layer of glazing to clean. And so depending how these are deployed, it can be either a minor addition to your maintenance workload or a more significant addition. But overall, what we expect is that when you build a more efficient building, you get more durability and longevity out of the building components. Here, what we're looking at is the expected life of usage for the equipment. For a lot of renewables, you're looking at a 25 to 30 year lifespan before you have to completely replace it, put in a new system, or there's a significant refurbishment of materials or components of that system that's approximately equivalent to the cost of just replacing the system. We're building envelope components. Usually the core components of the building, the structural components, can last for a decade or more. A century or more. Many decades though, at least twice the life expectancy of most renewables. There are components like roof surface structures membranes, things like that, that have a 20 to 30-year life. But it's a relatively low cost to replace just that one component over the entire roof. Similarly for fenestration, typically after 20, 30 years, you start having seal failures, things like that, that's going to degrade the performance of those windows. And it might start to be cost effective to look at replacing those fenestration systems after that time frame. But again, approximately equal life, and if you've got good, well-installed windows, even slightly longer life than most renewable technologies. And so again, you're offsetting long-term maintenance costs for replacement and end-of-life costs of the equipment as far as disposal, recycling. Building automation efficiency is kind of, again, this one exception. If you're doing, installing building controls and just letting them run, we've seen those systems needing significant upgrade or commissioning requirements with even as short as a year, 6 months. But typically, if you're not doing regular commissioning, you're just doing basic maintenance on an automation system, you get about a 5 to 10 year life. If you've got a comprehensive commissioning plan, you can get slightly longer life out of those controls. But as technology advances, we get more software improvements and things like that. They do tend to have a limited lifespan for building controls and will require replacement within about 10 to 15 years. But again, what we're looking at here is you're offsetting with more efficient buildings. You build that efficiency into the structure. That's going to last on average about twice as long as if you put in a renewable system. 20 to 30 years, now you've got to replace that renewable system with a new component. But we do want to note it's going to take a combination of strategies to reach a net zero future. Solar energy is generating that mid-afternoon peak energy. With some storage, you can offset that to match some of the building loads a little bit. Efficiency is going to drop your building loads overall, so that renewables, one, you can reduce the capacity that needs to be installed, and two, you open up a little bit more load flexibility as well. With building controls, you can shift building loads around a little bit to better match renewable productions and align generation capacity with demand. So a combination of all these needs to be done, but again, efficiency is doing that overall reduction of total energy that's going to last significantly longer as well. So before we move on, we've got another, I think that poll is going to come at the end. Do not have a poll yet, but we can take a quick pause here to look at some of the questions that may have come in. It was mentioned earlier, building enclosure commissioning is going to be a code requirement. Is that base building code or for the zero codes? Base building codes are going to require commercial buildings to have air leakage pressure testing done. In other climate zones, there are some exceptions, but in Illinois climate zones in particular, those exceptions don't apply. And so every building will need to have pressure testing done. That's coming with the 2021 IECC and the Ashrae 2019. Is solar for hot water no longer considered viable for Illinois? It can be viable. The one thing that I caution designers about solar thermal systems is if you design so that you meet your thermal loads with solar thermal, there's periods of the year where you're wasting that generated energy. You're going to have excess thermal capacity that it's much more difficult to find a way to use that thermal energy in a building. Like in the summertime, if you're doing solar thermal for hot water, you don't need that heat in the building generally somewhere else. You're doing cooling at that part of the year. But if you design so that your thermal loads meet during peak conditions, then when you have non-peak conditions, now you've got to supplement your thermal energy from another source. So it's not that it's not viable, but it's trickier to make effective use of solar thermal options.
And similarly with hot water systems, what we're seeing is a trend more towards heat pump systems. And the downside of using the vacuum tube or other solar thermal collection systems is the only thing you have there is there's only one thing you can do with it. Whereas if instead looking at pairing heat pumps with renewables, that renewable electricity, it can go to that heat pump, but if the heat pump doesn't need it, then it can be used for many other aspects. And so that's where we've kind of seen a shift there. It also generally simplifies construction and installation by kind of migrating more towards the heat pumps. The solar collectors may still have a good application. One one application I could think of would be, if I'm trying to heat a pool and say, okay, let me try to supplement and add some additional heat to this. So there may be applications for it, but again, the lack of flexibility can be a problem.
And then we did have a comment here about geothermal ground loops can have an upward of 100-year life expectancy, which is true. They can have that life expectancy, but the associated pumps and the heat pump system itself that's tied to that loop does have a 20 to 30-year lifespan associated with that equipment. Something else is geothermal, as far as the renewable energy credits and renewables applied to buildings. I believe that's referring to geothermal electric production on a utility scale. It's not referring to geothermal use on site at a building for heating and cooling purposes necessarily. That would be more of an offset type of strategy.
And something that is a good point to bring up is with a lot of these systems, understanding that the different components may have different lifespans, and being cognizant of and acknowledging that. Because with geothermal, you do have a ground loop that may be able to last through 2 or 3 systems, but you do have to replace the internal systems for that. I did notice earlier, I touched on this, but I don't think I fully finished the question as far as the windows and how do we manage shading for buildings taller than 1 story, where trees and plants, landscaping can be very, very effective on a 1 story, maybe even a 2 story building. But then looking at, okay, how do we deal with buildings taller than that? And that's where you get into either external shading devices or internal light shelves, where you're trying to reflect the light, take advantage of light when it's useful and not when it's not. And that's really, again, this is part of being cognizant of and being judicious about where fenestration is located, and understanding that the play, particularly now as we are, more and more surrounded by technology, and making sure that we're, we don't need to. We do want to have views to the outside, but I don't need a 10-foot by 10-foot window to accomplish that. And so being aware such that people can locate their devices and monitors and screens in such a way that they're not having a giant window that's blasting them with light. And then that's where alternatively to internal or external shading, that's when you can get into blinds or more preferable electronically dimmable glazing. But it's really nice, but that gets expensive, and that's another thing to repair over time. So again, being aware and saying, being able to provide people the flexibility to use the spaces as they find useful.
I did have a poll for this section. I scrolled right over it. The question was, why should designers focus on building efficiency before applying renewables? Reducing demand and thus reducing required renewable capacity. Efficiency is typically lower unit costs in renewables. Efficiency has minimal added labor and maintenance costs, or all the above. We have a couple more questions come in. One about the grid. If we're moving to all electric, how is the grid going to manage those loads? Part of that, with on-site energy generation, the building's going to use the energy directly. With net metering, you do have to account for some of that's going to get fed back into the grid and credited back to the building later. And that feedback does need to be accounted for. Right now, utilities have capacity mapping on their grids, so they know where they can tie in renewables and how much can be tied in before there's going to be a major issue with feedback to the grid. For offsite renewables, a lot of times that's coordinated with utilities as far as tying those into the grid. But it's going to be a long-term process of not only adding the renewables in appropriate places on the grid to balance demands and loads, but also adding some means of storage capacity to the grid as well. So that, again, you can shift generation to match when actual usage is needed. It'll be a long-term process, but we do need to start with making our buildings as efficient as possible.
Yeah, and that's kind of where that last slide that we had kind of touched on really comes into play, is saying, can we bring our building loads down, and then can we make buildings a little more flexible as far as when they're using that energy, and finally, yeah, storage, and we oftentimes we think about we need a giant battery for storage, or things like a giant bank of batteries to do this energy storage. However, as the future technology that we're seeing kind of coming down the pike, so to speak, is there's going to be that parking lots full of batteries, which then you get into vehicle to grid, where, hey, if the grid's short a little, hey, can I borrow a few kilowatt hours? Can I borrow 5 kilowatt hours out of each of these batteries? That's a lot of energy, and then okay, I can put that back later. So that's where storage is really going to come into play, and understanding that this is going to be a long-term transition. I said earlier, saw the article that came out this week, or the noting state of California this week passed 98% renewable generation for a period of time. And so understanding that as we make this transition, and as the grid can become more flexible, that's going to play a major role. Fortunately, it isn't going to happen overnight, but in the terms that utilities generally deal in, of 50 to 80 years, it's going to be really fast coming, and they are doing research as far as how are we going to handle and manage that change. Do see a question here about cost of renewable energy credits. The cost can vary rather dramatically depending on the type of rec and how specific you are. And so if you were to just say, I want I want to be able to buy recs for to cover my building of a totally generic, I'm not specifying, the only thing I'll specify is it has to come from the continental US. We've seen those be, a penny or less per kilowatt hour. I think I might have even seen them for like 1/10 of a penny or 2/10 of a cent per kilowatt hour. But if you say, I want a renewable energy credit that was for a system started in the last 2 years in the central Illinois region, solar array, because as you're getting more specific, the pool of available credits shrinks and your price goes up. Which that's part of the reason why you saw in those earlier tables, the less specific you are, and the more you just say, well, I'll buy them as they come, you end up getting penalized for that. Whereas if you make that direct investment up front, there's a much more guarantee, and so they don't penalize that as much when you're counting.
They did clarify their question was the cost of the rec as needed to meet the baseline requirements for the zero code, which I think falls kind of along the same lines. It depends on what rec you're specifying. But as far as like a unit cost to add into budgeting a building construction, not quite sure. It can vary.
Yeah, and that's there again, that's one, the less specific a rec is, the cheaper it is, but the more the code penalizes you, and so you have to buy more of them. So it's kind of a balancing act there.
But as far as our poll, looks like everyone got the correct answer. All of those are reasons why we should design for efficiency before we want to apply renewables to our buildings. All right, I will turn it over to Ryan to go over on-site versus off-site renewables.
All right. So as far as looking at on-site and off-site, looking at that from the operations, building operations standpoint, along with procurement, and I will touch on state of Illinois' incentives here when we start talking about procurement here. Obviously, when you've got on-site solar, we don't have to transport it anywhere, so we're avoiding our transmission and oftentimes delivery fees for on-site solar, so you're able to get much more direct utility cost savings. On-site solar can give you some independence from the grid if you do have on-site storage. Most of these systems are not designed to island themselves, as it's called, where in the event of loss of utility power, they can go into an island mode and isolate from the grid and continue to operate and supply that electricity to the buildings. Most systems don't have that feature, such that when the grid goes down, and really what it's looking for is that 60 hertz clock cycle. When you lose your utility grid, it goes into a safe mode and says, okay, stop production, and your building goes offline anyway. It's also beneficial, for your marketing, of being able to show, the people coming to your building that, hey, we care about renewables, and here they are right there. Do have several downsides, including the maintenance. Little less so on panels. Panels, it's more about inspections and things like that. But inverters and other equipment may have ongoing and annual maintenance required. And they can make cleaning and snow removal difficult, particularly if you have solar canopies over parking lots, and also the aesthetics. Some people don't like the look of solar panels. Other people love it. So, that's another one of those considerations. Rooftop, because you are adding weight. Fortunately, solar, since we deal with a lot of snow loads in most of the state of Illinois, the added structural reinforcements generally not too high, but being aware that that's there. But if you put it on the ground, then there's a lot more, landscaping and ground maintenance for that. And canopies, over parking lots, again, the snow removal can be an issue. And the big side is they're more expensive. On-site wind, again, we don't have transmission fees and anything like that. These can have a smaller footprint than PVs, and again, highly visible. The issue you run into is available wind resources are fairly low for this. And so these, and as Sean alluded to, these can require some heavy equipment to do maintenance. A lot of cranes, as you know, if you need to lift parts of these off, can be rather heavy. So again, aesthetics, that's again a judgment call depending on different people's viewpoint, and trying to integrate the turbines into buildings can have a lot of challenges there. So typically we see renewables procured offsite. The nice thing is, if you procure offsite renewables, typically there's a third party dealing with any of the maintenance, as you're normally buying those through a power purchase agreement or other utility contract. Again, you don't have quite as much impact on the direct facility, but the downside is, since it's offsite, you got to pay to get that power in, and you cannot be grid independent. So that's not even an option for that, and you don't have the visibility of making that statement, of being able to show people, renewables are important to me. It's not quite the same when people ask and you say, hey, I got renewable energy, and people ask you where it is, and you say, well, you go about 300 miles west and hang a right and you'll see it. And utility grade, utility scale renewables do have wilderness and wildlife impacts. Fortunately for solar, we have seen this being transitioned away from the gravel pad that everything is sitting on, over towards more of a planted bed, and a lot more pollinators and nature friendly, native friendly species through there. So we have seen that transition here. So as far as building operations, if you're doing on-site, you get that direct use of energy. It's really clear. But if you're doing on-site, it takes land and takes area to do it, and you have to add maintenance to that. Whereas, if you're doing off-site, you don't have to deal with that in your building design and things like that, but comes at a fee and a cost for that. Some of your procurement options, if you're doing on-site procurement, most of the time we see this done through net metering. You can do some export. Generally, the terms aren't very favorable if you do end up having to export electricity. With that, again, because it's directly metered, so you have it directly offset immediately, so you're not having to trade back and forth and do a lot of mental accounting, if you will. And the nice thing about on-site is they're generally a permanent part of the building and site. Whereas if we look at more off-site, you can just purchase electricity from off-site, which is perfectly fine. And the issue can be trying to actually get a hold of the RECs. And this can also be a issue when you're dealing with on-site renewables. And I mentioned I will bring up the state of Illinois incentive programs that are out there for renewable energy. How those generally function is those are buying the renewable energy credits. So if you're taking advantage of the adjustable block program or Illinois Shines program, that you can no longer claim your renewable energy because you have sold off that renewable energy credit back to the state of Illinois. Those credits are then bought by the utility companies to meet their renewable energy requirements. But just so that you're aware, if you take advantage of the Illinois incentive programs, you no longer can claim your RECs. And when we look at the accounting for procurement, again, when it's on site, very straightforward. It's net metered, or the PPA, you're purchasing it directly, so there's not really an issue there. Again, the only thing there is are you retaining and retiring the RECs yourself? Because oftentimes with a PPA, you can buy the electricity and not the RECs, or you can buy the electricity with the RECs. So, again, with this, zero codes, they make it very straightforward. It's a one-to-one, so you don't have that. Okay, well, I have to derate my credits by any amount. If you're doing offsite, not only do you have to try to verify that, but also being able to trace and track that, and we've touched on a few different times that procurement factor can really dramatically shift that math on you. And so being able to understand, okay, what type of renewable energy am I getting, and how much do I have to derate that to see if I've met the net zero or not. So again, on-site, really easy and straightforward. If you're doing off-site, it can get a little bit more mathematical on you. So with that, I believe we've got one final poll here. So first question is looking at what are the primary benefits of on-site renewables. Choose all that apply. No transmission fees or line losses. Net metering can provide the credits for excess production. Does it reduce maintenance requirements for the building owner? High visibility for marketing and publicity, and does it simplify building design? Second question, what issues can arise with off-site procurement of renewable energy? The RECs can be lost when the building owner changes. Purchase of renewable energy credits may not generate new renewable capacity. Excess generated electricity is lost without benefit. And off-site RECs can be attributed to other sites by a utility, can potentially be attributed to reattributed to other sites by a utility. Ooh. One question I would have for folks, and you can just pop this in the chat, is any net zero buildings that our audience has been a participant of. It would be interesting to collect a little bit of a listing of some of those that you guys have been a part of, and perhaps be able to recognize some of those accomplishments and achievements. Looks like last couple of people are voting here.
Okay, looks like that's most everyone there.
All right. No transmission fees or line losses for on-site renewables. Check. Net metering can provide energy credits. Sounds good. Reduces maintenance. No. And high visibility. Definitely yes. Simplified building design. Not so much. So good. People did pick up on that. And then issues with off-site procurement. Renewable energy credits can be lost. Yep. Purchased RECs does not guarantee new capacity. That's correct. Excess generated energy is lost without your benefit. Sure. And off-site RECs might be reattributed to other sites by a utility. Could be. So yeah, so a little bit of a trick there on the last one. All of those can be yes. So good to see. We've got at least a couple of people. We've got some zero energy design going in for Heartland Community College, breaking ground. So that's good to see.
Looks like we got a couple of hands up on the participant list too, that indicating they've been involved in some zero energy projects. And UIUC's retro commissioning team has done some significant energy improvements to the electrical and computer engineering building on campus.
Yeah, so this definitely can show that, yeah, the issues that, yeah, the simpler we can make our buildings, the more durable they become. So
I don't see any questions that have come into the chat or the Q&A, so I'd like to thank everyone for joining us today. Again, this has been recorded. The recording will be available after the presentation. You will receive a follow-up email with a certificate of completion or attendance, the slide deck, and you'll be able to apply for your AIA continuing education credits through a link in that email. So thank you all for joining us today. We hope you have a wonderful rest of your afternoon.